Hello everyone, Rabi here from RK Software Solutions. Today we are presenting on coupling beams using the Strut-and-Tie method, which is getting adopted widely within the Australian industry to comply with the Australian standard at Section 12, where the span to depth ratio of the beam is less than 3. I'm presenting in this video a complete workflow that is useful, and I encourage everybody to share this video to spread the word. The application that we are having is the deep coupling beam, which is part of the STM calculator. We'll be talking about it in a bit. But before that, I'll just scroll to talk generally about the behaviors of coupling beams or link beams or header beams, whatever you call it, within a shear wall or within a core. We all apply modifiers in our models, ETABS models essentially, and those modifiers are to represent the strain or cracking on the beams that are induced as a part of the lateral loads. Now, if you make your beams very soft, the shear, like modifiers F11, F22, M11, M22, etc., and ETABS, if you make them very soft, you get a scenario for the distribution of shear along the height of the building that is mostly uniform from the bottom third all the way to the top. And if you put a lot of stiffness in your beams, so like the relative stiffness is too high comparing to the wall, then you get the maximum shear that will be lumped in the bottom quarter or bottom third. That is widely known in the literature. Now, that is the overall behavior. So when you're reading your ETABS model, you will find always the maximum shear will be within that spot unless your beams are very flexible. Now, what happens essentially is you have two scenarios where you've got earthquake load combinations and every other load combination. When the building is less than, I'll say, 30 stories, so the beams will be governed most probably by shear on earthquake, and you need to apply overstrength for the design of the shear in order to comply with the Australian standard. So that scenario, you'll need to put overstrength, so you up the shear force essentially by a factor that we'll be talking about in a bit. And you don't apply it for the flexure because you want the beam to fail on flexure, crack, ductile failure before any snapping failure on the shear. Another scenario where you've got other load combinations, for example, wind loads as a lateral loading, that would be without overstrength because the ductility concept here doesn't apply. You're not reducing the loading to trade it with ductility. The overstrength factor in the current Australian standard, you've got this clause 14.66, which is very ambiguous. It was talking about the walls. So this is under walls. There is no specific clause about coupling beams. So it was currently people debate as to what overstrength factor that you need to apply. Some say go to mu over SP flat, and that will get you up to 2 or 2.1. Sometimes 2.6 people I see applying, which is an overkill, and others apply this clause, which is essentially gonna yield at 1.6 if you try to minimize your flexural reinforcement. So it will be exactly equivalent to the moment applied onto the beam itself. Now, with regards to the new standard, our code writers colleagues have finally clarified that, and you've got the overstrength factor is getting 1.2 times m over m, or 1.5, the lesser of both. So you're not likely to get the reinforcement exactly equal to the demand. So, but you need to make sure that your flexural reinforcement is as less as can be in order to achieve a sensible overstrength factor. The approach for Strut-and-Tie on beams is not new. It was announced or invented by our colleagues in SOM when they were designing the Burj. At that point of time, they were designing to ACI 31A, some old version, and that had the limitation on the maximum shear stress that is applied on the beam. So they've come up with this model, which is the Strut-and-Tie model for beams that many people recognize, where you've got the ties are the dark ones there. That is representing the flexure, and this one represents the shear, the tension in a beam in a vertical direction. Everything else is struts, and you've got nodes, at the wall nodes, if you want to call them, or middle nodes. So that is the approach that we are having. In our calc, we've cited this reference, and you can enter all of the parameters, thickness, depth, clear span of the beam as it shows in your geometry, and you nominate the width of the middle node and width of the wall nodes. The black ones are the wall nodes, and that will be the depth of the reinforcement. If you've got, let's say, 2 layers of reinforcement, we'd recommend 80. If you've got 1 layer of reinforcement, probably you make it 30 or 40 or 50 as the center of gravity for the group of reinforcements. Now, this is the overstrength factor in case you are dealing with um, seismic scenario, and that essentially is inserted so you can reduce your flexure RIO by the ratio of overstrength factor. But you need the force to be 8 equivalent to the equilibrium. So you've got 973 here, 877 because you've got 650 divided by lever arm, you get this value, and 720 divided by lever arm, you get that value. So that is not reduced by the overstrength factor because the model won't be in equilibrium. You can't feed the shear directly. You need to feed the moments because the shear must be worked out by the formula V equals M M1 plus M1, M2 divided by 2, essentially. Now, what happens? You've got as well, so you've got all of the nodal checks. So the end product will be what is the reinforcement that's going to be applied for shear, and what is the reinforcement applied for flexure. And if you are very keen, you can check the struts themselves. Um, um, by clicking on calculate and then going to struts. So you can do the strut exactly like what the Australian standard requires. But if you are very keen, just remember that this beam here is super confined element. And if you might appreciate, the Australian standard might give concessions on those very confined elements where you can up the factor for strut capacities. Now, what matters in this example is our flow procedure. So whenever you've got ETABS analysis, so you get it to spit out the moment values and shear values essentially, and you export them to Excel sheet, and you can use your own workflow within Excel predominantly. So that is one approach, but it won't be comprehensive because not all of the offices have tools dedicated for Strut-and-Tie. And here where our application comes. So what you need to do is do the following. So I've got here the batch solver. Click on this one, so you get this window, and I will load an ETABS file, an Excel file there, which is W9, for example. In this, I will be importing all of the coupling beam numbers. So that will take the shear applied onto the beam, and then will put the equilibrium moments on left and right of the beam, because the whole purpose is designing the shear itself. Once you're done, you just solve all of the beams in one click. So here we've got, for example, 4,000 cases. So we've in our calc we've selected 75 where you've got the maximum shear application from those load combinations. And in this scenario, all of the beams have passed. You might be having like a different challenging scenario where the beam width is not 350. Let me just do it, and then just make that 250, for example, and open and apply current values. So everything becomes 250, and then we batch solve. So now the solver is working. So you've got, let's say, 17 beams here have failed, and you can investigate. So what you can do then, click on Excel button. So you will have a file saved. In this file, when we open it, you will get all of the summaries, so all of the beams that you've got, the critical load combinations essentially, and that is the grand summary. So here we have two beams in this Excel sheet. Uh, enable editing. So there, if I just filter B number 12, which is this beam here, maybe this is 12 and this is 13 in this very wall. So what you'll see, whatever the beam per level, so you've got tie spacing being 210 and flexural reinforcement is 1000, for example, and that's the ratio. Wherever you've got a beam struggling, then you need to look into the depth or the width or MPa in order to pass the nodes, and it will tell you the critical load combinations. Just one very important thing there that you need to when you are importing from ETABS, just import the beams that have the same working span and the same depth at the same time. Otherwise, you won't be able to apply the current parameters. So those parameters, 50, 500, etc., and especially the span, thickness, and the depth. When you are doing the batch solver, you're doing it for those numbers. So you might have uh, 50 beams in a wall, for example. They share the same depth and the width and the thickness. Then you can do it. And this is what I would always do: just design one wall at a time or one beam at a time. A very convenient tool, and share this video if you find it useful. At the end of the day, if you are doing just one beam off, you can um, close that, and you can generate a calculation report after activating this strut. So you need to first of all calculate, activate the strut, and then go to calculation. So it will generate neat and nice calculation report. This concludes the example. It will be loaded together with the walkthrough, detailed walkthrough on our Calc website on the Learning Center. We've got now 4 topics covered, 3 videos on FECalc, where you can model and design a warehouse, and we have Strut-and-Tie wall, as well as column load rundown and sizing tool, quantity takeoff, which is very useful for those interested in quantities scheming at the early stage of the project, and sustainability. This concludes the example. Thank you very much.